The last strategy for factoring polynomials is to recognize polynomials that are quadratic in form. So the standard form of a quadratic is au squared plus bu plus c. But if I let u be something else, like u could be x squared or x to the 5th or x to the 9th, if I let u be something else, then I can build a new polynomial that, because the degree is higher, it's not a quadratic anymore, but it is still quadratic in form, which means we can factor it using the same strategies that we did for a quadratic. So here's a couple of examples of how that works. If I let u be x squared, remember it's au squared, so that's a times x squared squared, plus bu, so that's plus b times x squared, plus c. When we do a power of a power, x squared squared, we multiply the exponents, so that results in ax to the 4th plus bx squared plus c. That is not a quadratic, it's a quartic, but it is quadratic in form. It follows the pattern of a quadratic, okay? If I were to let u equal x cubed, we would replace the u's with x cubed, and we end up with a times x to the 6th plus b times x to the 3rd plus c. Now here's what I want you to notice. Here's how we recognize when they are quadratic in form. Notice they always end in a constant, okay? That's really important. And then the second thing that I want you to notice is that the middle exponent is always half of the first exponent. So this is half, 4 divided by 2. This is half, 6 divided by 2. We get 3. So that's kind of what you're checking for. Now it could also be a sum or difference of squares or a sum or difference of cubes. So you want to be careful there. How do you know if it's a cube, if it's not just a third power or a square? Any power of x is a perfect square if the exponent is divisible by 2. So for example, for this first one, if I have x to the 6th, that's equal to x to the 3rd squared. X to the 20th would be equal to x to the 10th squared. You divide it by 2. That's how you know it's a perfect square. A perfect cube would be something like also x to the 6th, but it would be the reverse. This would be x to the 2nd cubed, or x to the 12th would be x to the 4th cubed. If you can divide it by 3, it's a perfect cube. So those are the things that you want to look for. One strategy for doing this is to use u substitution. This is something that we use often in math to take something that is kind of a complex, ugly problem and rewrite it in a form that is simpler to work with. We can work on that simpler problem and then put the ugly piece, whatever u was, back at the end. So here's an example using u substitution. And I should say, this is just one option of how to do it. I'm going to show you another option in just a second. If you're not loving this, don't do it. Some people really like this strategy. Some people really, really don't. So, do whatever is more comfortable for you. But so the idea here is I check, this is a constant, and 4 is half of 2. So that's how I know that this is quadratic in form. And so remember, the quadratic standard form is au squared plus bu plus c. So whatever this is attached to the b, that's what we're going to choose for u to be, okay? So that's why we let u equal x squared. Once I've decided that u is equal to x squared, now I can write it as a quadratic using that standard form. And then we can factor that like normal. You would use factoring by grouping here, but we factor that and we get 2u plus 1 times u minus 9. But our original question was in terms of x, not u's. So now we're going to substitute u equals x squared, and that's how we get to this form. Everywhere that there was a u, we put an x squared back in. And then we check to see if we can factor anything further, and here we can because we have a difference of squares. And so that's how we get to our final answer here. Now, we can just kind of brute force this without doing that substitution, and I'll show you that right now. Sorry, I didn't get that paused in time for the bell to ring. So here's the other option. If you want to do this without u substitution, okay, then that means we're just going to start with the original 2x to the 4th minus 17x squared minus 9. We've already verified that this is quadratic in form, and so that means we're going to treat this just like we do with a quadratic. So first times last, negative 18, and then negative 17 on the bottom. I get negative 18 and positive 1. Now what we do with those side numbers, remember we use those to split the middle. Now remember, the middle term is an x squared term. So when I split it, I need those values to be like terms. So I'm going to say minus 18x squared plus 1x squared. Okay? These have to match x squared, x squared, x squared. They have to all be like terms. And so from here, now we're going to do grouping just like we did before. So I can factor out a 2x squared. That gives me x squared minus 9. I can only factor out a positive 1, and I get x squared minus 9. Common factor is x squared minus 9, and we're left with 2x squared plus 1. And then again, difference of squares, so we get x plus 3x minus 3 times 2x squared plus 1. Either method is fine. It's just a matter of like, which way do you see it? Which way makes more sense to you? One is not smarter than the other. One is not quicker than the other. They're the same amount of work. It's just a different strategy. So it's completely up to you what you like. Let's look at a couple of problems. Okay, so we want to factor completely. And again, we're always going to check first for a GCF. And so on number 3, there is a GCF. I can divide everything by 3p squared. And that gives me, oops, these variables are supposed to match, by the way. Let's change this p to an x. And we'll go with that. So now we have x to the 6th plus 5x to the 3rd plus 6. Okay, now again, we check, is it a constant at the end? Yes, it is. And is the middle one half of the first one? Yes, it is. So that is quadratic in form. It is also nice because a is equal to 1. So that means we want to know what multiplies to 6 and adds to 5. That's 2 and 3. Now the question, though, is what are our factors going to start with? When it was a quadratic, we just said x plus 2 and x plus 3. Okay? But that is because the middle term is always what the factors start with. So this right here, x to the 3rd, that's what each of these has to start with. Remember, that splits the middle term. So our factors are going to be x to the 3rd plus 2 and x to the 3rd plus 3. And there is our answer. Always the middle is what your factors will start with. Okay? Now, number 14. Let's look and see if there is a GCF. And there is not. Nothing goes into 16 and 81. And so now I see two terms with a minus. So this could be the difference of squares, or it could be the difference of cubes. Since 4 is an even number, we can divide it by 2. That means this is a perfect square. Okay? So I divide it by 2 to see what I squared. Sorry. So this is 4x squared squared minus 9 squared. I know it's x squared squared because I divide the 4 by 2. And so we now have 4x squared plus 9, 4x squared minus 9. This last one is the difference of squares again. So our final answer is 4x squared plus 9, 2x plus 3, 2x minus 3. Make sure you're always on the lookout for those difference of squares. Pause your video and try number 15. We'll come back and do 16 together. Okay, so we have a GCF of 5x squared, and then we are left with something quadratic in form in the middle. It ends in a constant. Middle is half the first. And it's also an a equals 1. Notice that your factors after that start with the middle term, so they both start with x squared. Now, those are both differences, but they're not perfect squares, 2 and 3. So that means that we are done. That's the end. Now, 16 is a little bit trickier. So again, I see two terms and subtraction. So let's first check if it's a difference of squares. Is 6 an even number? Yes, it is. So that is a perfect square. But 8 is not a perfect square. So this is not a difference of squares. So then I want to check, is it a difference of cubes? Is x to the 6th a perfect cube? Yes, because I can divide this by 3. That means that this is 6 divided by 3 is 2, so it's x squared cubed. And then 8 is a perfect cube. That's minus 2 cubed. So we're going to use our difference of cubes rule. So remember, the pattern is a squared, b squared. And then we SOAP. Same sign minus, opposite sign plus, always positive plus. And then we plug our stuff in. So a is x squared and b is 2. So I get x squared minus 2. X squared squared, we multiply the exponents. That's x to the 4th. Plus x squared times 2, which is 2x squared. Plus 2 squared, which is 4. Now, I should check this guy and see if it is factorable, but it's not because that's not a difference of squares. And so this is our final answer. Okay? To me, this is the hardest one. So this is the hardest one to get the hang of, watching for this pattern and knowing what you're looking for. So it just takes practice. Do the homework. Try to wean yourself off your notes so you can make sure that you're getting to that level of demonstrating. And let me know if you have any questions. I'll see you later.